In this video, we'll look at two problems about motion graphs and how we can extract information from them. This first problem will be based on position versus time graph, and it's asking you to extract a lot of different information from this graph. I strongly advise you to try it on your own before looking at the solution. So to do so, just hit pause now and come back once you've worked out all the problem. Part A. At what time or times is the train changing direction? When we look at the position versus time graph, a change in direction of the object will correspond to a change in direction of the curve itself. So in this case, it only happens once when t is equal to 2 seconds. When t is equal to 0 seconds and when t is equal to 10 seconds, we don't know what's going on after or before, so we cannot claim that it's changing direction. B. During which interval is the train slowing down? Well, on a position versus time graph, if we want to have information about the velocity, we want to look at the slope of the tangent line. So if we want the train to be slowing down, it means that the slope needs to be getting closer to 0. The slope is constant in the first part, constant in the second part. So the only place where it actually starts to become flatter is in this region in here between 6 and 10 seconds. So our answer in here will be that it will be slowing down for times that will be the interval 6 seconds to 10 seconds. If you really want to be picky, you could claim that at exactly 2 seconds, it will actually slow down. But we'll come back to this once we sketch the graphs. C. What are the speed and velocity at t is equal to 1 second and 4 seconds? Well, to find that, we have to remember that velocity is given by the slope of the tangent line when we're dealing with the position versus time graph. And when we look for the speed, well, it will just be the absolute value of the velocity. So in here, the first point where we try to find information is at t is equal to 1 second. So since it's on a straight line, we can just pick a second point, maybe at 0 seconds. And from this, we can easily calculate the velocity by calculating the slope. So velocity of x at t is equal to 1 second will be equal simply to the position at 1 second, so 0 meters, minus the position at 0 second, which was 4 meters. And we want to divide by the difference in time, so 1 second minus 0 seconds. So when we do the math, we get minus 4 meters per second. And I remind you that this was for t is equal to 1 second, which means that the v at that moment will be equal to 4 meters per second. That's the speed. Then we can do the same analysis when t is equal to 4 seconds. And for t is equal to 4 seconds, let's pick 2 new points. You see, we're still on a segment of a straight line. So we can take, let's say, at 4 seconds, 6 seconds. So in here, when we do the analysis, we'll get that Vx will be equal to the velocity at, let's say, we start with 6 seconds. So 0 meters will be the position minus the position at 4 seconds, which is minus 2 meters. So we divide this by 6 seconds minus 4 seconds. So if we do the math, you see minus minus will cancel out. So we'll be left with 2 meters over 2 seconds, or if you prefer, plus 1 meters per second. And the speed, in this case, will be exactly the same since it's already a positive value. D. What is the acceleration at 1 and 4 seconds? Well, between 0 and 2 seconds, the position is changing uniformly. So it's a straight line that we see in here, which means constant velocity. And if the velocity is constant, then this means that there is no acceleration. And at 4 seconds, the exact same analysis can be done. So the same will be true there. Between 2 and 6 seconds, there is no acceleration either. At 8 seconds, however, we do have an acceleration because the slope of the tangent line keeps changing. And to find the sign of the acceleration, you have two options. Okay, you can look for the change in slope for the tangent line. And in here, you can see that if we draw a tangent line at 2 different points, we could have one tangent line, let's say like this in here, and then a little bit later it will look like that. So you can see that the tangent line gets more negative. It was fairly positive at the beginning and it will go towards 0. So the slope becomes more negative. which means that the acceleration has to be negative. Another way to see this is to just look at the shape of the parabola. The shape of the parabola in here is clearly open downward, right? So it's part of a frowning face. And remember what we've seen before, when you have a parabola that is opening downward, we know that this corresponds to an acceleration that will be smaller than 0. So negative acceleration once again. Part F, what is the displacement between 0 and 10 seconds? Well, for that we just go back to the definition. Displacement is just the change in position, so we take the position at t equal to 10 seconds, which is 2 meters, and subtract the position at 0 seconds, which was 4 meters, so the displacement is minus 2 meters. To find the distance covered during the 10 seconds, it's a little bit more complex, because distance, remember, adds everything, it never decreases. So it first goes from 4 to minus 4. So this means that the distance covered will be 8 meters. So from 0 to 2 seconds, we'll have a distance covered of 8 meters. And then from 2 seconds to 10 seconds, we have an additional 6 meters covered. So this means that the distance between 0 and 10 seconds will be equal to 8 meters plus 6 meters, or if you prefer, 14 meters. Part H, we want to find the average speed and average velocity during these 10 seconds. You have to be careful. Often people try to find the speed at one moment, speed at the other moment, and then just take an arithmetic mean of all of that. That's not how to do it. What we want to do is to go back to the definition. The average speed is just the distance over the time elapsed. So in here it will just be 14 meters per second, 14 meters, divided by 10 seconds. Or if you prefer, 1.4 meters per second. And when we want to look for the average velocity, it will be essentially the same calculation, but for the average velocity, we'll take the displacement instead of distance. So we'll have minus 2 meters over 10 seconds, which will bring us to an average velocity of minus 0.2 meters per second. And last portion, we want to sketch the corresponding velocity and acceleration versus time graph. So let's start with the velocity graph. So I'll add my label in here as well as the units. Although I don't really care about numerical values in here, it's mostly the shape of the curve that I'm after. So this one is not too difficult. The first portion between 0 and 2 seconds, you see that we have a straight line, which means that the velocity is constant. And we know that the slope is negative and fairly steep. So I'll put just a constant negative velocity in here. Then after 2 seconds, the velocity becomes positive because the slope is positive. And you see that it's not quite as steep as initially. So I'll draw it a little bit smaller, but positive this time. And then at the end, we have the slope of the tangent line that slowly gets to 0. So my velocity will slowly get towards a 0 value. I'll just wrap it up by adding a vertical line in here. I remind you that in real life, this line is not truly vertical because it happens over some interval of time, even if small, not being 0. But in here, I'll just show it as a vertical line. So essentially, that's what we get. I want to bring your attention to the fact that earlier I said that actually at 2 seconds, it's kind of slowing down the object. And you can see that it was going at 4 meters per second of speed before 2 seconds, and then it drops to 2 meters per second. So indeed it slows down, but it happens over really just 1 instant. So if you don't include this in your analysis, it's not a big deal. But you will see that it generates something interesting on the acceleration versus time graph. So let's look at this graph. So the acceleration versus time we know will be in meters per second squared. And the velocity is constant between 0 and 2 seconds, and it's constant between 2 and 6 seconds as well. So what we would expect is just a constant line going from 0 to 6. However, there's something interesting that is happening at 2 seconds, because the velocity suddenly changed there. It suddenly becomes more positive. So if the velocity becomes more positive, this means that we have an acceleration there. But the acceleration is pretty large, but happens over just a short amount of time. So what we will get is just a peak like this, a peaked acceleration. And in here, the acceleration, the sign of the peak is positive because the delta V that we observe is also positive. All right. And then it's back to 0 until 6 seconds. And then from 6 to 10 seconds, you can see that we have a negative acceleration, as we said earlier. And then it's constant until 10 seconds. And that's it. So in general, this is not too difficult, but this jump in here that corresponds to the kink that we have in here will bring you a peak in your acceleration versus time graph.